In this video, I'll show you a tool that will make your work life infinitely easier and more efficient. This tool is called RAG, Retrieval-Augmented Generation. Here's why you should care. This tool will save you time because RAG is like a supercharged search engine that quickly scans through all your documents, pulling out the information that you need. And it gives you clear and accurate information, and ultimately it boosts your productivity. So you've got time to focus on important tasks within your organization or within your business. Now we're going to build it from scratch, so follow me as I go through. Let me talk you through the technology. So here on the left hand side, you're like the user, you type in a query and you're querying documents that you have within your business. So these documents could be contracts or any white paper or some official documentation. And if you've got many documentations to read, or even just one with many pages, you don't really have the time to search through. So what you do is you have this document loaded into your database or your LLM, and then you send questions through, and what happens is that the LLM responds with answers to your question based on the context of that document. So this is what it looks like. Send a query, the query is converted into embeddings, and those embeddings are saved in your vector database, and then your vector database takes searches for any similar context or similar information to the query that you've sent, and then it returns chunks of information that match your query, and then passes all of that information to your large language model, which then converts that into text that you can understand. So let's have a look at what that looks like within our solution. So first, let's look at the tech stack. So the stack that we're using to build this we have got a Google compute engine. So that's the server where we would install all of the software that we use for this. Now, the reason we're using Google is because the vector database that we're using for this solution is a Postgres database, and that database needs to be installed somewhere. We've chosen Google Cloud or Google Compute Engine for that. And if you're getting started with Google, they provide a $300 credit that you can use for these types of tests, and that credit lasts for 90 days. So we've got the server or the instance, which would contain Postgres. Postgres is the database that would hold the document when you upload it into your system, and would hold all of the vectors and the indexes relating to the documents that you want to search. Llama Index is the LLM model that we're using in the background, and then Hugging Face is where the embedding model would be sourced from, and Llama Index will come from Hugging Face as well. And then Llama Index itself, Llama 2 will come from Hugging Face, that's where we're sourcing it from. Llama Index is what will pass the document into different chunks and then loads those chunks into our database. Okay, so this is where the code begins. If we look at the beginning here, we're setting up the environment. So here, we'd install all of the packages, Python packages that we need in order to complete all of the RAG information. So you've got the reader, this bit here, this is a package that reads PDF documents. The document we'll be looking at will be a PDF document. And these are the packages. They're all coming from the Llama Index stable. You've got the Postgres package. You've got the Hugging Face connecting to the Hugging Face portal. Then you've got the Llama CPP. So this version of Llama of Llama from Meta is V2, and we'll see that being installed later on. So the next thing. So this portal is called a notebook, and I'm using the notebook extension within Visual Studio Code. I'm connecting from my local machine directly onto the compute engine instance that I mentioned will be part of this solution. So the next thing we do is we execute the Hugging Face embedding to retrieve the embedding model. So the embedding model we're using here is the BGE Small English. So we execute that. So I'm not going to execute everything because some of these stages take a little bit of time, but this is us just setting up the environment. So here we're pulling the Llama CPP Python, and then this code retrieves the actual LLM itself. As you can see, this is the model URL. It's going off to Hugging Face, and it's pulling the all of the information that we need, all of the files that we need, down to the Google instance. So when it's there, we then install PostgreSQL. So as I mentioned previously, if we look at the diagram itself, the database in this case is our Postgres, and with our Postgres we'd also install something called pgvector, and our pgvector handles the vector information. So if you picture this, we've got a document that's loaded, whatever that document is. We use Llama index to parse those documents into different pages, into its constituent pages, and then those pages are broken down into chunks. So you don't really want to load all of those documents into just one chunk. You break down the document into different chunks so that the searching can be more efficient and would use less tokens, because the answer to your question typically will not be the entire document, it will be certain sections of the document. So what you're searching using RAG is the relevant sections that would answer the question or the query that you've sent. So so we look at Postgres is already installed, and then we prepare the database, we log in and create all of the users and the user accounts that need to be in place for this to work. And then we install pgvector, so that's Postgres vector, and that's what we need for the vector feature in Postgres. When you see these ticks, that means they've already been installed. So I've run most of these steps already so that this video doesn't go on forever. But yeah, as you can see, this one's taking a little bit of time. So that goes through, completes, then we install other packages as well. So the next thing is we create the database. We initialize the database. We then use pgvector to connect in and create a table. So this table is called a Llama 2 paper. Now the document that we'll be looking at for this RAG process will be a Llama 2 white paper. We can look at that a bit later. So here we download the document, and then we call it the llama2.pdf. So if we look in here, the PDF document is there. The URL is arxiv. Downloaded it earlier. Yeah, so arxiv. This is 77 pages long, and this will get parsed by Llama index into 77 different items within one of the arrays. So we'll have a look at that when that comes in. So we load a file using a PyMu PDF reader. Well, this is where we import it. And then we load the file, so the data llama2.pdf, into the documents array, and then we initialize the splitter. So this is what we use to split the document into its different chunks. When the PyMu PDF reader reads the document or the file that we want to query, it loads it into an array or a list of documents or a list of pages, and that list is 77 items, and those 77 items match the 77 pages that form the document. Now, as this section is enumerating the document, it's actually going through each page, and as it's going through each page, is using this text parser. The text parser is essentially our sentence splitter, and we've just defined here that each page will be split into different chunks, and those chunks are 1024 in size. So essentially we've got an object with 77 items in it, and each one of those items, which is each page, is then split into different chunks. And as those chunks are being created, it's populating this doc indexes array and the text chunks array. So here I've just printed out here so you can see. So I printed the document, what type it is. So this shows us it's an array or a list, and the length, which is 77 items. And then I'm printing out the different chunks that it's reading. So you can see index 0 is showing us one of the chunks. So here, one of the chunks. And then index 1 is another chunk, and index 2. So if we look in here, we can see that the document ID is this, and then it's now giving us the text, which it's classed as one of its chunks. So Llama 2 Open Foundation fine-tuned. If we go right to the top, that should be right at the top. So Llama 2 Open Foundation fine-tuned chat models. So that's this bit here, and that's being split into 1024 size. And that will carry on throughout the entire document. So by the time it's finished, the entire document, it then will create nodes, and it's those nodes that will get passed into the that'll be converted to embeddings and then saved or persisted to the Postgres vector database. So now, once that embedding is completed and stored, right, all these nodes, so that's where the embedding model gets the text embedding. So it's essentially embedding this information, and then once it's done, all of the nodes data would then be saved in the vector database. Okay. Right. Okay, so that's saved in the node.embedding, exactly. So the node.embedding field is updated with the information from this operation here. Okay, so all of that embedding is here, and then that's persisted to the vector database. And then we move on to the retrieval. So now we've set up the environment, we've embedded the document in and saved it to the database. Now the next thing is you want to then ask a question, any query you have, and you want it to pull that information from the database. So we start by creating something called a retrieval pipeline. So this is us retrieving the information from the database. So the question we're going to ask is, can you tell me about the key concepts for safety fine-tuning? So it's supposed to pull this information from the vector database. So let's go here. Right. So we've sent our query. So that's completed somewhat. And then if we print that information, so this is showing us the information that is pulled back. So this right here, if we look at the document, you'd see that this relates to some section of the document itself. If we search for it, okay. So the risk categories considered, and if you recall, the question that we asked was to do with the safety and the key concepts. So it's accurately matched our question to the most similar section, most similar section of the document, and has returned it. So once that information is returned, as we can see in this diagram, once the information is returned, then it, along with the query, is sent to the large language model. Then a response is generated in your natural language and then returned to the user. And that's it here, and that's the response we get here. So you can pull out different types of information from the response. You can see the nodes that were returned by the search or the query of the vector database. And then you can also see what embeddings were created for the query that was sent to the vector database. So all those nodes are then returned and then put into a retriever. That's what this section is doing. And then the retriever then defines what the retriever here, that's what's happening here. So the retriever itself is being defined. This similarity top K is just saying return the top 2 responses from the vector database, and then that would then be sent to the LLM. So top 2, and then here we're sending those responses to the LLM right here, and this is the query engine. So this bit here takes a while because the server I'm using for this is not a huge server, but so it's running now in the background. The query I've changed here to something else. So the query here is how does Llama 2 perform compared to other open source models. So it will be running in the background. I've already run that before, and the response it came back with was based on giving context information. Llama 2 outperforms open source models. So we can find where it got this information from when we look at the document. So Llama 2 outperforms, if we go over here, so this is the actual document itself. Let's find it. Llama 2 outperforms. Okay, so it's added some of its own text. Llama 2 outperforms all that. Okay, so the large language model has modified the information it received in order to make it more human readable. But what we should be looking for actually should be this additionally, comma, Llama. Yeah, there you go. So it's pulled it from this section here. So that's the information is returned. You can see that there's a slight error in the response because it says here Llama 2 outperforms all open source models on academic benchmarks, fine, with the exception of GPT 3.5 and Palm 2L on coding benchmarks. So it outperforms all open source models with the exception of that. So it gives the impression that it thinks that GPT 3.5 is an open source model, which it isn't. Now, if we look at the document here, what it actually says is Llama 2 70B outperforms all open source models, and then here the context changes, but it's cut that out for some reason. It might be to do with how the chunking has happened. Maybe it chunked here at this point here, so it hasn't quite noticed that the context has now changed to closed source models, and that's where GPT 3.5 fits in. But with all of these things, what you can do is be cleverer with the prompting and be cleverer with the how you create the chunks. So the chunks here are created quite in a very strict way. There's no overlapping. So there are different techniques that you can use to make your RAG system a bit more intelligent and a bit more robust. So things like overlapping, you can say, well, don't just cut so abrasively at 1024. You can have an overlap so that the context goes between the two different chunks. You may also decide to do more than just a top K of 2. You might want to go up to 3 or 4, and then once all that information is retrieved and passed to the LLM, we get a response back, and we also get the source nodes that generated that response, and that's what I'm printing here on the screen. So as you can see, I didn't have to read all 77 pages to get some idea as to what's in the document. And then with more intelligent RAGs, you can retrieve even better information and have responses to your queries produced for you a lot better. Now, the inspiration for this piece of work came from, is this Just here? I wonder. It's on Llama's website. Okay, can't find it now, but so, no, it's not this one. Okay, so there is a document that Llama Index produced, that's the inspiration for this work. I think this is it. Yeah, so building a RAG from scratch. And what we've done here is we've built a RAG solution from scratch using only open source tools, and we haven't had to pay for anything, not even the server itself. We installed Postgres and used it as the vector database. We use Llama Index for parsing the data. We relied on Hugging Face to provide us with the Llama 2 LLM model that we used. And what else is there? That's mainly it. So that brings us to the end of the creation of RAG from scratch. Hopefully you learned one thing or two from this whole process. If you're wondering what the IDE I'm using here is, or what this screen is, it's Visual Studio Code, and then I used the remote SSH extension to allow me program locally from my machine and run the playbooks against the server in Google Cloud. So if you have any questions, don't hesitate to ask. But until next time, keep winning.